Everyone can hear me? Okay, great. So hi, everyone. We are recording this meeting. Thank you for attending. So this is a session about Open Graph Benchmark Large-Scale Challenge that we are here at NeurIPS 2022. My name is Jure Leskovec from Stanford, and I'll do the opening remarks and present the program for today. This challenge was main organizer is Weihua Hu, who's just graduated from Stanford, Matthias Fei, Hong Yuren, Maho Nakata, Xiao Dong, and myself. So now to motivate what are we doing and why are we doing this? So we are really excited about modeling relational data, and the reason why we are excited about modeling relational data because it's ubiquitous, and interest in relational machine learning, graph machine learning is increasing, and it's one of the most important sub areas of machine learning today. So the question we wanted to ask is, how can we advance graph machine learning research? And the idea we came up with was what we call Open Graph Benchmark. So in May 2020, we introduced OGB, a realistic and diverse benchmark data sets for graph machine learning. The reason we call it open is because we actually have a community effort, and we think of this as an open benchmark that changes over time, and that community can contribute data sets and challenges. So it's a live object that is evolving over time as we are making progress in this important area of machine learning. And over last, let's say, 2 years, many different methods and techniques have been developed. Over 450 different submissions happened to our leaderboards, and there was very strong accuracy improvement on these data sets. We see, for example, between 17 and 22% improvement over what was state of the art when we started. But what we realized about a year ago is that we need a large-scale benchmark, right? So to yield the breakthrough in graph machine learning, we need larger graphs, larger data sets. So for two reasons: because machine learning on large graphs is challenging and requires more innovations, especially around training over large graphs, processing large graphs, non-trivial mini-batch sampling of nodes and edges, sampling negative examples, as well as building very, very expressive models that can take advantage of these types of large data. So we launched what we call OGB Large-Scale Challenge, which is an annual large-scale ML competition for large graphs. We have 3 tracks or data sets covering node, link, and graph level prediction tasks. We held the first edition of this competition last year at KDD, and this is now the second edition of this competition at NeurIPS 2022. So for this competition, we thought it was very successful. We had 180 teams who registered, downloaded the data, and worked on the models. We had 31 teams made final test submissions, so the final submissions, and we selected 9 teams as winners. Basically, we have 3 different tasks, 3 winners per task, so 3 times 3 is 9. We have a nice split between industry and academia. Interestingly, we get more submissions, more winners from industry, and then geographically we have 5 from China, 2 from UK, and 2 from United States. What is important for us is that we progress and improve as community. So a key to OGB is that winners release code and technical reports. So both code and technical reports are available so that others can reproduce and learn. And we make this publicly available at our OGB website, ogb.stanford.edu. You should definitely visit the website because you can learn a lot from this. Now, a bit more about the OGB Large-Scale Challenge. These are large-scale data sets that are orders of magnitude larger than what community was using before. We have a node level task, which is a Microsoft academic graph on 244 million nodes and almost 2 billion edges. A link prediction task over Wikipedia knowledge graph with 91 million nodes and 600 million edges. And then we have a graph level task, which is a molecular task with 4 million different graphs. And each of these tasks and data sets is realistic and very practically relevant. So to talk a bit more about the node level task, this is a heterogeneous academic graph of different papers, authors, institutions, and then we have citations and other types of relations. The task is to predict the subject area of a node in this heterogeneous graph. So that's a real world task here. For the link level task, we have the link prediction from the Wikidata knowledge graph. So we want to impute missing links that are of different types. What we have done here differently from last year is that last year for every possible positive link, we gave 1,000 negative examples. So it was an easier task. This year, we didn't give any negative examples. So each prediction is evaluated over, 91 million other potential negative examples. So it's a much, much harder task. So very excited about the progress here. And then at the graph level, we have molecular graphs where we are predicting an important quantum chemistry property, what is called the holo-LUMO gap of a given molecule. And basically, the way you can compute this holo-LUMO gap is by using quantum computation, and it takes hours to compute this for a single molecule. And the goal is to predict this property or model it using a machine learning model. And we could potentially do this, super fast, less than a second. So that's the practical motivation for here, which is basically speeding up calculation by building physics-based calculation by building a machine learning model. So that's what I wanted to say about the OGB large-scale challenge. What else to say is that here is the program for today. So I just opened with opening remarks. And then we have 3 sessions, each one of 50 minutes, where the winners are going to present their solutions. First, we are going to talk about node level track, the node level prediction. Then we are going to talk about the link level prediction. And the last part will be about graph level prediction. And we are going to learn about exciting new approaches that the winners took to make this possible. So with that, I'm going to hand off, I think, to Weihua, who's going to lead and moderate the network level track of today's schedule.
Great. Thank you, Yuri, for the introduction.
Thank you, Weihua.
Thank you. Great. Can everyone see the screen?
Yes.
Okay, great. So, first, let us start with the node level track. So in the first 5 minutes, let me briefly talk about what the dataset is about and how we constructed the dataset, what the machine learning challenges are for this node level dataset. So the node level dataset is called MAC 240 million. It's a heterogeneous academic graph with different node types, papers, authors, and institutions. And the prediction task is to predict the subject areas of papers situated in this heterogeneous academic graph, which can be cast as a node classification task. So how we constructed this data set? So we extracted 121 million papers in English from Microsoft Academic Graph. And each paper is encoded into 768 dimensional feature using the Roberta sentence encoder. Other than the academic papers, we also have 122 million authors who wrote the paper and the 26,000 institutions where these authors are affiliated with. So in total, we have the heterogeneous academic graph are like this. So what are the task details? So out of this 121 million academic papers, 1.4 million papers are archive papers, And these archive papers are annotated with primary subject areas. So it's these subject areas are come from this 153 archive subject areas. And you might be familiar with this kind of annotation for each paper. For example, cs.lg represents the area of machine learning. And the task here is that given the archive papers, new archive papers, we want to predict their subject areas, primary subject areas, which is basically multi-class node classification. To simulate this realistic scenario of predicting subject area of new archive papers, we split the data based on the publication year. So basically train models on papers published until 2018, validate performance on papers published in 2019, and the test performance on papers published in 2020. So given this, what are the challenges, machine learning challenges of this data set? So the first challenge is that this data set is really massive. We have in total over 240 million nodes and 1.7 billion edges across different edge types. And handling this using state-of-the-art graph neural networks requires us to use efficient sampling strategies to sample subgraphs so that GNNs can be tractably trained. Also, on this academic graph, we have rich feature representations. So you have this 700-dimensional feature over 240 million nodes, and in total we have around 400 gigabytes of storage. And handling this large feature and effectively retrieving the relevant feature for training GNN requires efficient I/O strategies. And handling this, training this GNN efficiently on this large graph potentially allows the team or to quickly try different ideas of machine learning algorithms. Now I'm excited to announce the winners of this competition node level track. The first place winner is Come Again team, which achieved accuracy of 0.7570, and it's from a team team members listed here. So Baidu, this consists of Baidu and the Tianjin University. The second place is a DSC node team, which achieves the accuracy of 0.7522, and it's from this Michigan State University and the New Jersey Institute of Technology. And the third place winner is CogDL team, which achieves the accuracy of 7.7506. And it's a team from Beijing Institute of Technology, Zupin AI, Tsinghua University, Anhui University. So congratulations to all the winners. And now we are excited to hear from the winners how they tackle the problem and what their solutions are. So I'm going to introduce each of the winners and then Q&A. Please feel free to write your questions in the chat, in the Zoom chat, so that we can ask questions to the winners at the end. We have 15 minutes a Q&A session at the end. So first, let me hand it to the Hongwei Chen from Come Again team. Hongwei, please share the screen and start your presentation.
Can you hear me?
Yes, I can hear you.
Okay. Can you see my screen?
Yes.
Yeah. Okay. Oh. Okay. Hello, professors. Our team is the first place winner of MAC 214 MChat. We are from the Baidu PGL team. This is the Hongwei for today's presentation. Our topic is boosting the speed and performance in training large-scale heterogeneous graph. Next, I will introduce this topic in the 3 parts. The first part includes some information of dataset and the test. The heterogeneous graph is from the Microsoft Academic Graph. The graph node includes the paper node, author node, and institution node. Graph node totally have the 240 million nodes. And we need to predict the subjects of given the papers. So that is the graph node classification test. The second part is our model. Before the model training, we prepare some setting to better utilize graph structure. In the lab picture, we use the Matplotlib to vector model to run the node embedding by different metapaths. We find that although the expression of graph neural network is enough, but there's still large improvement if you have this additional structural embedding. Follow the last year model. In the right picture, we sample the two-hop materialization subgraph for the paper sentinels. There is our model framework. This year, we added two strategies into our model. Position encoding for the graph and generalized PageRank. Position encode includes the paper published yes information and Matplotlib to vector node embedding. When we calculate attention score in neighbors aggregation, we plus the Euclidean distance of position encode. And the phi is a projection layer. This part just like another edge feature. Follow the generalized PageRank. After we get the all layer node embedding, H1, H2, and HK, we combine them by the generalized PageRank rate. This strategy is designed mostly to prevent the oversmoothing. This table records our single model best result on the validation dataset after we use generalized PageRank and position encoding for the graph. This one is the ensemble results by the model different setting. We get a 75.7 accuracy score for the text challenge dataset. In the last part, our major contribution is bidding optimization. That provides us with many opportunity to experimenting with different strategies for the graph node classification. This part includes the graph sampling and feature gathering. The first in the mini-batch graph sampling. In the previous architecture, we can sample on the CPU, but it is too slow. And we sample on the single GPU for the small graph. That is the faster. But the graph memory not enough for the large graph. So we need to compromise. We used two compromise strategies. One is sampling on the GPU, but store the graph structure on the CPU memory. That is UVA-based tensor technology. UVA is the unified virtual addressing. It accepts the CPU memory using the GPU. And another one is to store the graph structure on the multi-GPU memory and sampling on the multi-GPU. We can see the table 3. UVA sampling and GPU sampling are more faster than CPU sampling. Now a good question is how to share the graph structure on the multi-GPU memory. The second point, feature gathering can help GPU memory sharing. The Mac 214M is about 350 gigabytes. We cannot load all feature into the one single GPU device. So we need to split the feature into multi-GPU device. Each device can store the part of no feature. For example, you can, as you can see, 2 GPUs store the part of no feature, and we can exchange the all parts in multi-device. When we sample the subgraph for the one batch, we can only gather subgraph feature from the multi-device memory. No need the all feature. Compared to DGL in the lab picture, our PGL feature gathering on the GPU are more faster. The right picture records our model's training speed. Compared with last year model, we get the 36 speed up and finish training in nearly 1 hour. Here's some citation. That is all. Thanks.
Thank you, Hongwei, for the nice presentation. We will go to the next presenter, and we'll do the QA at the end. So we'll first move on to the next presenter, Yuko from CogDL team. Thank you so much.
Thank you.
Hi. Hi, I think I'm the
Oh, sorry. Actually, I was wrong. Hong Ziwen, please, from DSC Node. Sorry.
okay. Never mind. I'm going to share my screen. Hi, can you see my screen?
Yes.
Okay, thank you. Hi, everyone. I'm Hong Zhiwen from Michigan State University from the team DSC Node. And sorry. I'm sorry, there is something wrong with my laptop. Just go to the next slide. I cannot control it. Okay, sorry. Let me start again. I'm Hong Zhiwen from team DSC Node. I'm a PhD student at Michigan State University. And today I'm going to present our solution for the OGB-LSC node classification task. And the solution of our team is called inverse APUMP. I believe the organizers and the Winnie team has already introduced the datasets. So I would like to just skip this part and directly start from the model part. I think for most of the teams in this track, they choose the relational GAT or RGAT as their base models. And the RGAT is actually an adaptation to the graph attention networks, where they use different transformation matrix for different edge types. And there is a official baseline tables in the OGB-LSC paper, and we can see it. We can see from the table that those models start with R, which is the relational models, actually outperforms the non-relational models by a very large margin. However, we found that this kind of comparison is not fair, because those non-relational models are actually working on a graph that has only the paper nodes. But if we use a simple strategy to convert the whole graph, including the institution node and the author nodes, to a homogeneous graph, then in that case, the GAT can actually achieve a similar performance to the RGAT. And this observation is consistent with a team from last year, which is from DeepMind. So we are inspired from this observation that if we properly convert the graph, then the non-relational methods can actually achieve a similar performance as the RGAT, so that we want to focus on the non-relational method because they are simply more efficient. And we have an explanation of this kind of phenomenon. We think that the reason here that they can achieve a similar performance is that the other features in the heterogeneous graph is actually derived from the paper features. For example, we use the average of all the features of all the papers of the same author to be the feature of that author, so that the features on this heterogeneous graph is actually homogeneous. Given that we want to develop a non-relational method, we choose APPMP as our starting point because this is a very efficient model and it can achieve a sort of performance on many popular graph datasets. And the workflow of APPMP is to first use a MLP to transform the features, and then use a approximated personalized page rank to propagate the features on the graph. And they train the MLP along with the propagation. And what we did in inverse APPMP is to inverse the order of transformation and propagation, where we first propagate the features in the same way as APPMP, and we store the propagated features and train an MLP or a transformation over the propagated features. So the overall architecture is similar to SGC, where we use a different propagation rule. So the inverse APPMP can actually achieve a very competitive performance as a baseline model. So it can achieve a similar performance as GAT and RGAT. And since it's much more efficient than GAT and RGAT, we can use inverse APPMP to explore the different strategies. And finally, we will combine the RGAT and the inverse APPMP to achieve the better performance. So this is the base models we have, and then I'm gonna go through the engineer tricks we use. We start from a DGL implementation. So DGL is a very popular library for graph representation learning. And we implement the RGAT and inverse APPMP with DGL, and we try to add some tricks. For example, we first try to learn features for author and institution nodes instead of using the simple aggregation of paper nodes, paper features. However, that doesn't work. And we replace the GAT with GAT-V2, it improves a little bit. And we try to add a contrastive loss along with the main loss, which is similar to the last year team from DeepMind, but it doesn't help. And the other tricks we used are borrowed from the last year's winning solution, which is the RUniMP. We implemented with PyTorch by ourselves. And we didn't use the years of publication as PE. We didn't directly use that. Instead, we are inspired from our own observation. So we started the label distribution shift. So this is a significant issue in our data set. So here in this figure, we present 10 most popular topics, and each column represents the proportion of a topic or a class in a certain year, and different colors represent different years. So we can see that for the proportion of each class, it's different among different years, and it's not simply different. There is a significant trend in this kind of distribution shift. So this inspired that we can not only use the year embedding, and we can have some other different strategies. So we designed 3 different strategies to address this distribution shift. The first one is the loss reweighting. Since we know that the test sets is actually the most recent years, so we can, when training the models, we can give a higher weights to recent years. And the second one is the learnable year embedding, which is the same as the last year winning team, the RUniMP. And the third strategy is a fixed year embedding, which is borrowed from the vanilla transformer. We use a sign function to generate the positional encoding based on the year, since we observe there's a trend in the distribution shift. Eventually, we have so the performance is listed in this table. So we found that all of these 3 tricks can improve the performance of our baseline model. And if we combine all of them together, it can further boost the performance. Okay, so that is the tricks and the base models we have. And this is the final model we created. So actually, we combine the RGAT with APPMP, where we use the propagated features as the input, and we add the fixed year embedding to the features. And we also add learnable year embedding, meta path to VAC features, and also the logics of RGATs, which turns it to be a kind of stacking ensemble models. And since we are running out of time and we don't have sufficient computing resources, so we can only train 5 RGAT models and 5 inverse APPMP models with the cross-validation setting. So our final submission is simply the mean example of all these 10 models. Lastly, I would also like to introduce, since we still have time, I want to briefly introduce the method that we are still developing, and we might submit it to the public leaderboard later, which is the multi-view for GNN, where we design a new loss function that we want to optimize those 3 terms, which is like we want to preserve the features, we want to achieve the graph smoothing, and we use a alternating optimization algorithm to help us optimize the model. And the implementation is here. We already observed a significant improvement in our preliminary experiments, but we haven't finished it. Okay. So thanks for listening. That's all of my presentation. Thank you.
Thank you, Huangzi, for the great presentation.
I'm going to stop it. Please wait. Okay, thanks.
Okay, thank you so much. So let's move on to the CogDL team, presented by Yuko. Please go ahead.
Hello, everyone. I'm Yuko, a PhD student from Tsinghua University. Our CogDL team also includes Huanjing, Yufei, Zhengyu, Xiao, and Xu. I'm very glad to share our solution to the MAG track. The MAG DSS is the only one of 3 tracks that remains exactly the same with the KDE Cup 2021. Thus, we think it's very important for us to study the top solutions of last year. The top 2 solutions are UniMP and MP-NN plus BGIL are based on the message passing GN models and are not easy for us to reproduce due to the different deep learning framework and time-consuming training. The third solution uses unconventional algorithms to generate node features. So we take our eyes to the fourth solution, MPLP, which uses a simple and efficient model to obtain a good performance. So we use the MPLP model as our base model in our solution. The MPLP model uses a coupled architecture, which is similar to SIGN and NAS models. It first conducts feature and label propagations based on metapaths. It also uses of a baseline relational agility models. And a simple MLP model concatenates all the features for the final prediction. Further, it also uses a fine-tune trick to solve the unidentical label distribution. So in our solution, we'll add more effective features to the MPLP model. We first reproduce MPLP in our experiments. Then we get 75.84% accuracy on the validation set, which is similar to the reported performance. So we take the MPLP model as our base model. To further improve the performance, we explore many other features. For example, we add metabus vector embeddings into the input, and we get a better performance. Similarly, we explore other metapath schemas for the feature propagation. We use schemas of SEHGN from OGB-LSC and get similar performance. In addition, we also try different RGH embedding. We train a 3-layer RGH model and use the hidden representation as the additional input feature. We get a slightly lower but acceptable result. Finally, we ensemble 15 models with different feature combinations for the prediction. Each model uses 5-fold strategy to better leverage the validation sets in the training. We report the validation accuracy of each K-fold model in the slides. In addition to the NP-LP-based model, we also add the embedding of NP-N plus BGIL. Unfortunately, during the competition, we made a small mistake in generating the embeddings of NP-N plus BGIL on the validation sets. And so we get a high but false validation accuracy in our experiments. So as a result, the false but high validation accuracy leads to a weaker submission result of our model. After the competition, we fixed the bug and found that the correct accuracy of our submission is only 77.14%. However, if we simply average the predictions of all 15 K-fold models, the correct accuracy on the validation set reaches 77.56%, which is much better. Finally, we submit the prediction of test depth and get 75.35% accuracy on the test depth split. That's the experiments of our competition. To be honest, in the early stage of the competition, we met some challenges. For example, we are used to using PyTorch to write GN models, but the top 2 solutions of last year are all based on other deep learning frameworks. It is hard for us to reproduce them via PyTorch. Besides, training message passing-based GN models on such a large image dataset is really time-consuming, which is not friendly to us. Adapts a metapath-based decoupled GN model, which is both scalable and effective. We utilize different features to generate diverse models. Additionally, we combine the prediction of NP-N plus BGIL in our final submission. Finally, we sincerely thank Zhipu AI for providing A100 GPUs. That's all. Thank you very much.
Thank you, Yuko, for the great presentations. Great. So now we have 10 minutes. Actually, we have 20 minutes for Q&A. So if you have any questions, please unmute yourself and ask your question. So I can start. I can start with a very general question, like what are to each winner, like what is the biggest challenge when you do this competition, and what is the biggest surprise that you learn from participating in this competition? So first, like whoever is ready, maybe you can start. And so nurse, if you can open the video. and unmute yourself, that would be great. So is the question is the question clear? So what is the biggest challenge and what is the biggest surprise when you join this competition?
I think I can go first. Oh, okay. Hongwei, please.
You should unmute yourself, Hongwei.
Oh, okay. Our most challenging is we try to marry the strategy for the graph node classification, but many of them it didn't work. So we had to have some confused which point about the graph node classification we should be focused in the future.
I see. Is it like I saw your architecture stays mostly the same from last year, right? Is that because you tried other architecture and they don't work, or is it just you want to fix the architecture?
Yeah. We add the many stage strategy, but only one is only two. Only two strategy is what.
I see. And how about the GNN architecture themselves? Did you try to innovate there as well, or because your GNN architecture stays more or less the same from last year?
Okay.
I see. Even GNN architecture do not really matter too much in your experiments.
Okay. Thank you.
Interesting. Thank you. Next, whoever wants to go.
I think the biggest challenge, I think most of us, especially for the team, like, because we are academic team, right? Because we are from the university. So the biggest challenge, of course, should be the scalability and the computing resources limitation, because we don't have too many machines to try everything we want. So what we did is we start from a subgraph. So we use the graph partition algorithm to separate the graph. And we always, so during the exploration, we always conduct our experiments on a subset of the graph so that we can do the exploration. Because if we try to train a model on the whole graph, it will take several days. And we don't have too much time and machines to do that. And what we learn from this competition is, of course, because the most research, the complicated models will encounter a severe scalability issue in the real world application. And that could be the biggest difference between the research and the industry or the application. I think in the community, there are already many researchers that focus on the scalability, but I think maybe it's still not enough, and I would like to see more researchers that can target this kind of scalability issue in the future. Yeah, thanks.
Yeah, that makes sense. Thank you so much for sharing the experience. Yuko, do you want to go next?
Okay, thanks. As I mentioned in the last slides of our presentation, I think the biggest challenge is also the GPU. So from the top solutions, we can see there's basic parsing GNN models, much computing resources. But so we use a decoupled and a simple architecture, which could also get similar results. So I think for the largest image datasets, we could propose to use any simple architecture. Yeah,
that's really interesting. I actually find very interesting this decoupled based GNN still works even for heterogeneous graph with multiple node types and edge types, which is quite surprising to me. So yes. Very, very interesting observation. From the audience, please feel free to chime in when you have any questions. I can ask more questions. So for basically this decoupling based GNN, like especially for the second team, Hongzhi, like did you inject the node type knowledge somewhere, or you just propagate the feature along the homogeneous graph and use the resulting feature as the input to your MLP?
Actually, I also want to ask this question to Yuko, because I think for this kind of decouple method, it's not that convenient to include the node representation. So unfortunately, we didn't do that, but I think that is partially due to the property of this graph, because in this specific data set, I think there is no like feature heterogeneity. So that's why our method can work. But I think in the real world, there are many other like graphs would have very heterogeneous node types or edge types. In that case, we haven't figured out how we can adapt our like decouple GNN to that case. I think there is already some researches related to it, but we haven't started it.
We also borrow some ideas from the existing research, such as SEHGN. So we can use some metapaths for us to do the feature propagations. So for example, we can set up a PIP such as this metapath. So we can PAP or PAFAP, similar to this metapath, we can propagate the paper features to the other paper features. So the also works from my view. Yeah, thanks.
Makes sense. Yeah, you use a lot of the metapath information. Hongzhi, it looks like you literally treat everything as a homogeneous graph without utilizing much about this metapath.
Yes, so according to our experiments, for the baseline models, they're similar, but we do also we also noticed that the RGAT with the sophisticated tricks can outperform our baseline models. And I think like there is some specific tricks for RGAT, like relation-wise attention. So they are not available in the decoupled GNN. So I believe the upper bound of the like RGAT, this kind of relational-wise method should outperform the decoupled one. But since decoupled one is much more efficient and we can use it, like we can directly use the GAT feature GAT logics to do the stacking. This is just one solution. I think recently there were some papers to distill the knowledge from the GNN to MLP, but I'm thinking of whether we can also like distill the knowledge from RGAT to improve our decoupled GNN, but we haven't tried that.
I see.
But I think currently the RGAT can obviously outperform the other types of decoupled neural networks. Yeah.
Right. I agree that upper bound can be higher, but it's just way more expensive. And the question is whether we want to like pay this cost to perform better, because it looks like the decoupled GNN is already quite good. That's very interesting. And any questions from the audience? Okay, I will ask more questions. So for the Hongwei, you talk about several like architecture design to train GNN efficiently. And one thing is that you scatter the feature across different devices in the same GPU machine, and then you kind of gather those features on the fly. And basically, just my understanding is that you are utilizing this fact that like moving features across device within the same machine is fast.
After we get the speed optimization, we can try to marry different strategies. like the label propagation or like the label graph constructive learning or self-supervised learning, but many of them it didn't work. So we tried only get the two strategy is get the improvement in the accuracy score.
Oh, sorry, I'm talking about the infrastructure part.
Oh,
Talking
yeah,
about-
this part is keep the same with the last year model day.
Yes, not the model part. I'm asking the question about the fast training part.
Oh, this part, the graph sampling on the GPU and feature gathering split to multi GPU.
Yeah, so it's like transferring from, for example, device 1 to 2 within the same machine is super fast.
Yes.
I see. Interesting. Okay. Makes sense. And for the graph sampling, did you because I feel like edge connectivity information is probably just worth several gigabytes, right?
Because for the edge, it's not too large. The no feature is the no feature is the big problem in the in the multi-device to exchange their part.
I see.
The edge is we can use the trick to fix them. Yeah.
Makes sense. So you can always store all the edge connectivity into GPU, perform all the sampling in the GPU, and
yes, we can store in the multi GPU and sample on the GPU and get the fast.
Okay, so you never use CPU, almost never use CPU.
Yes, we because last year CPU is too slow, so we in this year we all put the whole graph structure tensor into the multi GPU there.
I see.
Save our times.
That's very wild idea. Very interesting. Okay, cool.
Yeah.
And also I want to encourage among winners to ask questions to each other if you feel comfortable.
Question for Hongwei. So the RUniMP model is very powerful, but are there any chance for us to reproduce the RUniMP on our own machines rather than the Baidu crowd?
Yes, you can reproduce. Because last year we only the 4 V100 machine. It on the CPU on the GPU is okay. So the main architecture is RGAT. So also we add another strategy on the RGAT. So and we open the code in the PGL GitHub. You can get the code in you can get from the GitHub there.
Hi.
How about the
I'm sorry.
the MetaPath method? The MetaPath method is trained on the CPU or GPU?
This part is on the GPU because we can sampling on the GPU, so we can faster to training that. Yeah.
Oh, thank you.
You can try to use pedal or PGL. Or after we open source the PGL box, you can sample the MetaPath on the huge graph. Includes some the billion, more than the billions nodes, or the yes, also 10 billion the age. We can do that.
Great. Thank you.
I'm sorry to interrupt, but actually we re-implement the UniMP with PyTorch, and it's in our it is already released in our repo, so you can check it. So we implemented with PyTorch, and I think we can reproduce the result of last year at least.
Thank you.
Okay.
Interaction. I have a question for Hongwei. Like, you are working in industry like Baidu, so I'm just wondering, like, how is it like to work on this data set and versus like your actual like production in Baidu, because Baidu probably also has large graph, and you also need to develop models for your own graph. How are they different experience, or you can share a lot of like experiences between large scale challenge and your own production, if you can share this?
Yes, this UniMP the model, we also the model has been used the many downstream tests in our companies or the our other companies, and we get a great improvement in the recommendation system that for all the website classification and many tests can use the graph node classification. Is very helpful for us. Yes.
Okay. So in general, you find something that works better on OGB, it's kind of works better on your own data set as well? Or did you find there are some discrepancy between this data set and your own task?
In our downstream task, the node feature is the big problem. The Mac 240 provides the robot embedding for the common but many the downstream tasks has no feature. Here maybe had the only the ID embedding, or the another feature is not enough to train the GNN. In this time, we will use the meta-to-meta train the node embedding for the after that we go to the UniMP model there.
I see.
This is a big gap.
Interesting.
No feature there.
No node feature in your own data set. That's very interesting. Cool. Okay, I think we are at this 2 p.m. Pacific time, and we can close the this node level session. Thank you again for the presenters, Hongwei, Hongzhi, and Yuko. Thank you so much for the great presentations.
Thank you for the organization.
Thank you, Weihua.
Thank you so much. Then I will hand it to Hongyu, who will lead the link level session.
Okay, thank you, Weihua. Can you see the screen?
Yes.
Very cool. So now let's move on to the link level prediction data set of the large scale challenge, and it's called WikiKG 90 million version 2. So WikiKG 90 million is a massive knowledge graph data set, and the task is to complete the missing triplets in this massive knowledge graph. So specifically, given the head entity, and the relation. The goal is to predict the correct tail entity. So in this example, we can see that given the existing information about Geoffrey Hinton, we would like to predict the missing fact that Hinton was born in the UK. So to construct this dataset, we extracted triplets from the Wikidata knowledge base that stores all this type of like encyclopedic facts about the world. And our dataset consists of 600 million triplets in total, describing 1.3 thousand different relations, about 91 million real-world entities. And each entity and relation also comes with a short description text. And we can also encode the text using this MPNet sentence encoder to obtain a 768-dimensional feature for each entity and relation, which can be used to help the prediction model. So as the knowledge graph is shown to be highly incomplete, our task is to complete the missing triplets in this incomplete knowledge graph. So specifically, given a head entity and a relation, we aim to predict the ground truth tail entity, and we use this time-based data split to simulate this more practical scenario of predicting new triplets that are not present in the current knowledge graph. So specifically, we train on triplets until May 17th, 2021, and validate triplets added between the May 17th, 2021 and June 7th, 2021, right? And finally, we do test all the triplets added between like June 7th and June 28th of 2021. And here we use the commonly used evaluation metric mean reciprocal rank. This is really commonly used in the KG completion literature. And the idea is that we want to have a higher MR or this mean reciprocal rank. And we think our knowledge graph dataset provides two significant challenges for the current graph machine learning community. So first, the dataset is again very massive with 91 million nodes and comes with rich features. And it is challenging to efficiently learn knowledge graph embeddings over such a huge number of nodes. And moreover, the model needs to do extremely fine-grained prediction, right? Finding this correct target entity among more than 90 million candidate entity nodes, which is also the biggest difference between the OGB large-scale challenge, the link level challenge this year, and the link level challenge last year in KDD 2021. Now I'm super excited to announce the winning teams on the link level track. And the first place winner goes to the Wiki team from the Graph Core research, achieving an MR score of 0.22562. And the second place winner is DNA KG team from Microsoft Research Asia, Peking University and University of Science and Technology of China, achieving MR score of 0.2514. And the third place winner is TIEG Yupu team from Tencent, achieving this MR score of 0.2309. Yeah, congratulations to all the winner teams. Okay, now let's get started with the winners presentation. We'll first start with Alberto. We'll first hear a presentation from Alberto Catania from Wiki team. Alberto, are you there?
Yes, I'm here.
Okay, cool. Now, please feel free to start your presentation.
Thank you. Can you see my screen?
Not yet.
Sorry. What about now?
Shows you started screen sharing, but I still cannot see your screen. Oh, yeah, now I can see your screen.
All right, thank you. Thank you, Angio, for the introduction to the task. Thanks to all the organizers for this brilliant competition and for the workshop. I will introduce the presented solution that we developed at GraphCore with our team WikiWiki. So we've already had an introduction to the task, so I can skip this preamble. I just want to recall how knowledge graph embedding models work. So the idea is that in order to predict missing links, what we want to do is to have some measure of the plausibility of triples and relation tails through some scoring function. And the idea of knowledge graph embedding models is to train embeddings for entities, for all the entities and all the relations in the knowledge graph. The plausibility function, the scoring function, is then a function of these embeddings, and the embeddings are trained in order to maximize the plausibility of triples, of positive triples in the knowledge graph, and to minimize the scoring function of negative samples that are constructed by randomly corrupting the tail of positive triples. And then at this point, when given a query head relation, in order to predict the tail, we just transverse the whole graph, looking for the entities which maximize the scoring function of the triple. So our solution is based on 4 main ingredients. First of all, we invested a lot of resources in developing a completely new distribution framework for knowledge graph embedding models, which allows us to achieve a very high throughput, both for training and inference on GraphCore IPUs, accelerators. This results in a final model that is an ensemble, a very large ensemble of knowledge graph embedding models, and a very diverse ensemble. So we are combining different scoring functions, different loss functions. The third important ingredient is a smart sampling strategy during training, motivated by quite a stark difference that I will explain in a bit between a stark distribution shift between the training set and the validation and test set. And finally, well, for instance, we use actually a very basic strategy, the one I was mentioning before. So no candidate selection methods are used, but then the predictions of the different models are ensembled in quite an innovative way that is also very general and not at all tailored to the specific data set. So let me first spend a few words on the distribution framework that we developed. So of course, with graphs of this size, we want to distribute computations across multiple workers, but then we have the problem of these very large embedding tables that we need to store and that are accessed by the workers in a very sparse way, because only the embeddings for entities and relations that are present in the batch need to be accessed and updated at each training step. So our distribution framework, which is called BESS, which stands for Balanced Entity Sampling and Sharing, is based on efficient and balanced collective communications directly between the workers, which in our case are the 16 IPUs of GraphCore Beaupod 16, each of which has access to dedicated memory storage across which we partition, we split, we shard the embedding tables. And with the key features that the workers can communicate directly with between them through high bandwidth IPU links in order to share the parameters. So the benefits of this distribution framework are multiple. So first of all, we can achieve a perfect balance in workload across all the workers, while retaining a variety of triples and of negative samples occurring in the same batch, which is very beneficial for the final embedding quality. And then, as I mentioned, the importance of balancing communications through collective operators directly between the workers. So no need for the additional parameter servers to manage these communications. And moreover, this also gives a constant communication cost at all training steps. So now coming to the models themselves, as I said before, we have a very diverse collection of knowledge graph embedding models. They all share the same embedding encoder strategy. So we have these trainable embeddings that I was mentioning before, but as Ongyu mentioned in the introduction, we also have for all entities embeddings in the dataset these MPNet text features. So the way that we combine these two components for entities, we are just summing together the trainable component, the trainable embedding, and a linear projection of the text features. While for relations, we are all just using a trainable component. In terms of scoring functions, we use 5 well-established scoring functions in the literature, 3 that are distance-based, transit, trans-h, and rotate t, each paired with either L1 or L2 distance to increase the variety of models, and then 2 similarity-based scoring functions that are dismalt and complex. And for losses, again, multiple choices. So the log sigmoid loss with adversarial negative sampling, which is again quite commonly used for this kind of models. And then sample softmax cross entropy, which is a bit less, I would say, a bit less used, but which also proved to be quite effective for this task. So I was mentioning before that during training we use a particular sampling strategy. The idea is that, as shown in the picture on the left here, when looking at the distribution of relation types between the training data set, the blue curve, and the validation and test data sets, this is quite different. So it's quite a large distribution shift. But when taking the cube root of the training frequencies for relations, we see the orange curve aligns much better with the distribution in validation and test set. So what we did is just during training, sampling triples with a probability that is proportional to the cube root of the relation frequency in the training dataset. And as shown in the second picture on the right, this helps a lot in closing down the gap between the training MRR, the solid curve, and the validation MRR, the dashed curve, compared to the standard flat uniform sampling strategy that is the one shown in red. And this gives a boost on validation MRR quite significant, up to even 2.5%. For inference, as I was mentioning before, we use a very basic strategy. So no candidate selection methods are used. Our best distribution framework allows us to perform inference very fast, and so we can afford to score all queries against all possible tails, so all 90 million plus entities in the knowledge graph. And then for each model, the 100 most likely tails, so the ones achieving the best scores, are returned T1, T100, ordered by decreasing level of confidence. So then the problem is different models will then return different sets. This 100 set of 100 tails will be different for the different models. So how we combine them in an ensemble. And the idea is to use a generalization of reciprocal rank fusion, introducing a power hyperparameter. So we call this power rank ensembling strategy. So the idea is that we fix this negative power hyperparameter, and then each model scores each entity by the power, the pif power of the rank predicted for that entity by the model itself. If the entity is among one of these 100 predictions, otherwise it will assign the entity a score of 0. And then we are summing together the scores for the M models that we want to ensemble, and then just taking as final predictions the entities which realize the top 10 values of this ensemble score ST. And the choice of this power hyperparameter was done just by sweeping. So in particular, we chose p equal minus 0.5, which seemed to be the best, and also seemed to be quite sensible and well-grounded from a theoretical point of view. So now to summarize our final result, so thanks to our very efficient distribution framework, we were able to train a very large number of models and to sweep hyperparameter quite extensively. So our individual models, final individual models, already achieve a very high validation MRR compared to the state of the art in the leaderboard previous to the competition. Then for the ensembling, we observed some interesting facts. So first of all, the fact that this power rank ensembling strategy scales quite well. So even adding weaker models, individual models to the ensemble still gives good performance up to very large ensembles. So as shown in this picture, when ensembling the KBEFS model of each of the scoring function compared to the single, even if the single models are shown in the dashed line, the curves for the ensembles are almost monotonically increasing when adding models that are individually quite weak. And moreover, we observed that in particular, this multi and complex performed quite well in ensembles, both when considering ensembles of the single scoring function. So you see again on the left, ensembles of dismal model or complex model, even if the model themselves are weaker than other distance-based scoring function, come up on the top in the end. But also when pairing pairs of different scoring functions, as shown in the heat map on the right, the best results that we get are in these regions here, where we are pairing dismal or complex with one of the distance-based scoring functions. So our final model is an ensemble, a large ensemble of 85 models based on the evidence before, which use 25 transient models, 25 dismal models, 25 complex models, and then a smaller number of translation relative. And these are the kind of the ranges of the hyperparameters that we consider, and the performance of the single models themselves that ended up in the final ensemble. So this is all. Just if you are curious to look at additional material, this is a link for where you can browse our code on GitHub, read the paper on which is available on arXiv, and also at this link very soon we will make available a paper-space notebook where you can try out firsthand our models and our new distribution scheme on IPUs. Thank you very much.
Yeah, thank you so much, Alberto. Let's follow. Let's thank Alberto again. We will also delay the Q&A session after the 3 presentations. So next, let's welcome Xiaojun Ma from DNA KG team to present their solution.
Okay. Please wait a minute. Well, can everybody see my screen?
Yeah, we can see your screen.
Okay, hi everyone. This is Xiaojun Ma on behalf of the DNA KG team from Microsoft Research Asia. And today, let me introduce our solution. And here's the agenda. First, I'll introduce the background of our solution and give a detailed introduction, and then the result and conclusion. And first, I just briefly introduce our thinking of this year's data sets. Compared to last year, the number of entities, relation, and triplets all increased a lot. And the most challenging change is that no candidate set is provided this year, which means we need to select the true tail from more than 90 million entities. And naturally, we will think if we can generate a similar candidate set, we can easily reproduce the good result of last year. However, it is not so easy because in last year, the 1,000 negative tails are a sample from the 90 million entities, which means lots of them are not similar from the true tail, and we can distinguish the difference easily to some extent. And this year, no matter what kind of method we take, the generated candidate entities must contain large amount of entities that are similar to the true tail. In our solution, the candidate generation module plays an important role. In summary, there are 3 main components. First, the candidate generation step is added to reduce the computation costs on the entire entity set. And second, various strategies are utilized to score each candidate tail. And finally, the fine-grained hyperparameter searching during the ensemble step. And we adopt 2 kinds of candidate generation methods considering 2 points. At first is the graph structure is critical for knowledge graph completion. True tails are usually close to the head. For example, in most cases, the shortest distance between the head and tail is shot in the graph. And second, multi-hop results will exponentially expand the race and raise memory and computation overhead. And the second is determining like rule-based strategy is also useful, which enjoys a high accuracy with small candidate size. And in detail, we in the structure-based strategy, we first create a tail set DI for each relation RI, and the K is the union of the training triplets and validation triplets. And notice that we did not use the testing triplet here. And then second, we generate candidates for query HRI according to the in degree of the tail that has been sorted in this order. And finally, we select the candidate size balancing between the hit rate and the computing cost. We can see it in the graph that the hit rate on the validation set grows as the candidate size increases, and we choose 20,000 as our candidate size for the structure-based strategy. And in the rule-based strategy, we take this to predict the unseen triplets in the knowledge graph. Here we provide an example. If X is the mother of Z, X is married to Y, and Y is the father of Z. First, we in detail, we divide the training graph into 5 subgraphs that mine rules by AMIE, and from the figure on the right, we could observe that the partial completeness of assumption confidence affect the mining rules. And for the most queries, the rule mining generates 0 or 1 candidates. Therefore, we treat the rule mining candidates as the complementary to the structure-based candidates. And second, in the scoring function module, we evaluate the probability of the candidate tail T given the query HR. The example shows the procedure given the query Microsoft Research as entity and including as relation, we score the entity in the candidate sets. Basically, we can get the final prediction by the probability, and the scoring function contains the model-based and the feature-based method. We take the traditional knowledge graph embedding methods as the base module and try different variants of them. We have 2 observations here. First, using MPNet feature with additional MLP is hard to achieve high MR on validation sets. And second, large batch size, more negative samples, and training steps helps. In the feature-based scoring function, we take the similar method as last year's winners. We make some modification according to the characteristic of the WikiKG 90 million version 2. First, we cut some feature compared and only generate the feature-based score for the validation set and testing set in the inference. Then we take each score as a result from a single model, and given the 23 scores from the knowledge graph embedding methods and the feature-based scoring, the min max is applied to score them from 0 to 1, and the coefficient search range from the 0 to 1 with the TPE tuner, and the NNI is utilized to accelerate hyperparameter searching. And here we give the link of NNI, and the results we can see it, in the graph. Left is the hyperparameter searching curve, and the horizontal axis denotes different trails, and the vertical axis is the ensemble MRR. And the right is the hyperparameter of each knowledge graph embedding methods and corresponding MRR. We can see the NNI does find the best combination of coefficient, and in the end we reached the highest result at around 3,000 trails. Here we give some observations as conclusion. First, candidate generation plays an important role in the imputing missing triplet task. Not just the quality, but also the diversity matters. As we found, even though we can generate a candidate set with higher hit rate, but the results did not get higher compared to the one using in the current candidate sets. And the second is the role of semantic embedding. As we showed before, using the MPNet feature with additional NLP is hard to achieve higher MR on the validation set. However, introducing MPNet feature in the candidate generation stage helps increase the hit rate. Maybe the jointly training the semantic feature and the knowledge graph embedding may help solve the problem. Okay, and that's all of the presentation, and thank you for listening.
Yeah, thank you, Xiaojun, for the presentation. Okay, now let's welcome Feng Nie from PIEF UPU team.
How to, okay.
Feng, can you please share your screen?
Oh, wait a second, I will setting first.
Yeah, take your time.
I might need to log out first and re-log in. Sorry.
Okay.
Sorry. Why? There's some. I've already give the.
What's the issue? Is there anything I can help?
Yes, but the preference it's always indicating that I have not set the preference. Okay. Okay. Can you see my screen now?
Yeah.
Okay. Sorry for the.
No problem.
Okay. Hello, everyone. I'm Feng Nie. I'm from Interactive Entertainment Group of Tencent. Today, I will present our team TIEG OPU and gives a solution for link prediction task on the second version of OGB-LSC released dataset. My presentation contains 4 parts. First, I will briefly introduce the link prediction task and the major challenges we met during the competition. Then I will introduce the retrieval and the re-ranking solution to tackle the above challenges. The last part will be the experimental result of our proposed method and give a summarization of the experience in this competition. So first come to the task definition. As you mentioned before that knowledge graph currently presented with multiple triplets, each head and tail entities are connected with a specific relation. The task of link prediction is to make inference on existing knowledge graphs. For example, the avatar, given the head entity avatar and the relation starring, the tail entities can be actors that participate in this film. So what's the major challenges we met during this competition? One obvious challenge is that the knowledge graph is really large. It contains more than 90 million of entities. If we want to search the answers who start in avatar, we need to compute the similarities over 90 million of candidates with head and relation vectors. It is quite slow. Also, we observed that in the knowledge graph, there are some frequent relations. Each relations can be connected to more than 10,000 entities in the knowledge graph. This kind of relations is more ambiguous than other kind of relations and is therefore more difficult. We also, during the competition, examined some state-of-art graph embedding models. We find that it is the single model is not quite good towards some complex relations. For example, some relations are much harder, like graph grandfather is kind of composition of father of and son of. Single models may not perform well towards all these kind of complex relations. To tackle the above challenges, we first want to solve the efficiency problem. We therefore follow the idea of large-scale recommendation system by proposing a retrieval and a re-ranking model for link prediction task. During the candidate retrieval, we want to improve the quality of for some top frequent relations. We therefore propose a multi-way candidate retrieval strategy that use both structural information and semantic information to improve the recall result. After retrieving similar candidates, we are able to design the graph embedding models. And we find that different graph embedding models can be complementary during the experiment. So we train a lot of state-of-art graph embedding models and combine them together with model ensemble to improve the robustness and generalization ability. So first, I will introduce our retrieval model. Retrieval model contains 3 parts. It is a multi-way retrieval model, which contains first using structural retrieval and semantic retrieval. Then to aggregate all the results, we design a priority infilling ensemble method. First, how to leverage the graph structure. We used one of the baseline methods using the latest model PIE. It is a relation prediction model where it randomly masks a few relations and regularize to inference relation with relation type and its surrounding neighbors. Once the relation model is trained, we can obtain most relevant and entities with highest posterior probability in this equation. However, we find that this method is not really good for some kind of top frequent relations with very low recall rate. To this end, we aim to directly use the graph structure instead by defining some working paths in KGs. Note that this is some quite similar idea that in the last year's winning solution, but we use it for the retrieval part rather than feature engineering part in this year. And by defining 13 working paths, including head to tail paths and relation to tail paths, we're able to add 13 retrieval models given the working paths. For example, one simple head to tail path is to compute the co-occurrence of one target tail entity and the head entities if they're connected within any relation in this knowledge graph. After the structural retrieval, we also actually it has been proven that some descriptions of the entity embedding can also help the link predictions on large knowledge graphs. For example, like the avatar description of avatar has already indicating what actors it participates in. So using this kind of knowledge is good. And we find that the data set has already provided with entity, with textual embeddings of each entity. Therefore, we define semantic similarity by computing the relation, by computing the distance between the relation entity and the tail entity. And then we adapt fast KNN search to retrieve semantically relevant candidates. And up to now, we have multiple models that retrieve similar candidates, and we want to aggregate them. But we find that majority voting treat each model equally, as a lot of retrieval models are rule-based methods. Some rules can retrieve quite similar results and will introduce noise incorrectly. To merge them more effectively, we present a priority infilling ensemble method. The priority is an accuracy that computing the percentage of the number of true candidates that retrieved with one model. And then we will aggregate results of different models with priority from high to low until we obtain 20,000 candidates. So up to now, we have retrieve similar and diverse relevant candidates for each head and for the query. And then we are able to design our graph embedding models. It contains two parts. First, we need to design the entity encoder. We believe that different strategies may help the graph embedding to capture different aspects of knowledge. We use three strategies. The simplest one is randomly initialized embedding. The graph embedding learned using this method only considers the graph structure. Another way is to fuse the randomly initialized embedding with some textual information. Then the textual information can be helpful for link prediction. Moreover, we propose to aggregate the surrounding neighbors' informations directly using for link prediction by summing the textual embeddings with its first order neighbors to represent the neighbor enhanced textual embedding and concatenate with randomly initialized embedding. As for knowledge graph models, we choose two types of translation method. First is trans-E. It is very simple and effective and can model one-to-one relation quite well. More importantly, it can allow us to set a really large negative sampling size and train with really long time and get substantial improvement. Surprisingly, we find this method, despite the simplest, but performs amazingly well in this competition. And the trans-E method is not capable of some types of relations such as symmetric and asymmetric. We therefore using some state-of-art methods like NOTE, which is the last year's winning solution and also complex to model some inverse, symmetric, and asymmetric and composition relations. And right now is the experiment part. First, we give the retrieval model result. As we can see that the structural-based retrieval is much better than semantic-based retrieval. And the rule-based, structure-based retrieval can be complementary with PIE models when directly using majority voting. And adding the structural priority infilling ensemble, we're able to gain one more point. although the semantic-based retrieval alone is not able to get a good recall result, but combining them with the structural based retrieval method will boost the performance. And for the re-ranking model result, we find that every single link prediction model, link prediction result is not really good, and the transient method is the best among all the other state-of-art method. But we find the largest improvement is that we need to ensemble all the results since every single method is not really strong enough. And we also find that applying a model selection on best scoring models can slightly improve the final result. So to give us our conclusion is that for the efficiency consideration, we propose a retrieval and then re-ranking pipeline method for link prediction task on really big knowledge graphs. And we also find that retrieval is very crucial for our link prediction results. So we leverage both structure and semantic information to increase the diversity, yet also semantically and structurally relevant candidates for the re-ranking method. Also, during the graph embedding model design, we find that incorporating diverse graph embedding models can lead to the largest performance boost. That's all. Thank you.
Yeah, thank you so much for the presentation. Yeah, now let's move on to the Q&A session. So I guess I can first ask start with a general question. Is that the biggest challenge you guys face for this year's challenge, especially like if you guys have participated in last year's challenge, right? Because like this year and last year we have a pretty big difference is that we no longer provide the candidate tail, but of course I know that for Alberto, you guys don't even need to do any candidate selection, right? And for Xiaojun, it seems that you've tried several methods from the previous challenge, but it didn't work. So yeah, just wondering about like some general learnings or challenges you guys face for this year's challenge.
Yeah, I think that yeah, for us we didn't participate last year, and as you mentioned, yeah, we didn't have a particular challenging from the point of view of having to select candidates. I would say the biggest challenge would be, well, first of all, of course, given the size of this graph, coming up with our distribution framework, a lot of thinking went into that, in order to guarantee a distribution scheme that was beneficial to the final embedding quality without imposing too much bias, while also being very efficient from a computational point of view. And also then I would say, given the diversity of models that we considered, find the correct hyperparameters for each of them. So very large sweeps for this kind of parameters. And if I can say something that actually was a bit surprised about, which is also partly a challenge, the way that how to incorporate the MPNet text features in the embeddings. So the ones provided by the dataset, as I was mentioning in my presentation, we went for a very basic strategy of just more or less summing together a projection of the text features with the trainable embeddings. But we didn't go for this just because we didn't try anything else. We tried a lot of other stuff. We tried concatenating the trainable and the projection, and then maybe passing through MLP layers or something like that, which is something that was done, for instance, by some of the winners last year. But yeah, we didn't really observe any kind of improvements on that side. So yeah, finding the best way of incorporating the text feature, I would say, was quite an important part of our work.
Yeah, that's really nice, a nice point, right? And also like a quick follow-up question to your point is that I also noticed that it seems that you guys didn't use the MPNet or the text features for the relations, right? I was
Yes.
just wondering.
Yes, that is true. Yeah, our assumption is that given that the text feature would be very useful for the entities, given the large number of entities, while for relations, we probably, yeah, we were assuming that it would probably not give too much of a difference in that case. Also based on this on these observations of how tricky it was to find the best way of incorporating the text features in general with the embeddings.
I see. Okay, yeah, that sounds great. So Xiaojun, do you want to share a bit about the challenges you guys face, and also especially, I think you guys also have some like new learnings of how to better utilize the MPNet, the text features. So I was also wondering about any learnings.
Yes, actually, same as the Alberto, we also try a lot of methods to utilize the MPNet features. However, when introducing the MPNet feature, we did not observe any improvements, which is out of our expectation. And this is indeed one of the challenging during the experiment. And another challenge is, I think, is the generation of the candidate sets. Actually, we spend a lot of time to generate the candidates. At first, we try to improve the hit rate, which means we want to get as more as possible the true tail in the candidate sets. However, we find when the candidate set size increase, even though we have a high hit rate, we do not enjoy the benefits of the high hit rate. So it's hard to balance the hit rate and the final MR in our experiments.
Yeah, that's a little bit surprising, right? Because like it seems that if you have a higher higher chance to get the final.
So we find maybe the diversity also play an important role in the link prediction task and for the WikiKG 90 million data.
I see.
Mm-hmm.
That's interesting. And Feng, do you want to share a bit as well?
Sure. First, I think our challenges with the other presenters are quite the same. First is the MPNet. We find that this textual embedding for graph embedding models is not always work, but it works for some kind of graph embedding models. For example, it is not workable for Trans-E. The Trans-E is better without MPNet textual embeddings, but surprisingly, we find that it is workable for a node graph embedding models. So I guess that is different because some different types of graph embedding models may be suitable for some kind of entity encoders. So that's why we use strategies for different models with different encoder strategies. That's the motivation. And it is also indicating us why and how the graph embedding model designs that will be different, acting different with different kind of embedding initialization strategies. And the second is that we find we try really a lot of time on improving the retrieval quality. And surprisingly, we also reached the same conclusion that not always the highest retrieval rate will lead to better results. And we find that diversity between the retrieval model design and the graph embedding model design in the re-ranking model is very important because we find that we train some strategies. We want to use the graph embedding models for the retrieval step in the experiment by setting different parameters and embedding initialization strategies to increase the diversity, but it fails sometimes. And we find that during the retrieval and the re-ranking design, there is better no overlap between two methods. So the more diverse will eventually get better result. So that's why we only use the graph embedding models for the re-ranking stage, rather including them in the retrieval stage, despite actually we end up finding that graph embedding models is more suitable for retrieval because it can really achieve high retrieval rate, more than 80 actually. But I have some new ideas on how to design the graph embedding models in the ranking stage. We think maybe the success to the large graph knowledge graph embeddings is to really try some better strategies in negative sampling, but because we didn't use multiple time for this competition, so I have no time to implement this idea. But I think the challenge comes to the negative sampling design, because it will better that we use not randomly sampled and active samples during the re-ranking stage, rather with some candidates that produced by the retrieval stage, but it has some high memory storage problem. So we haven't implemented this idea yet, but I think it's a promising research direction. That's all. Thank you.
Yeah, I think that's a really good point, right? So I think for this task, right, we really unless you have like a super nice distributed system, right, you have to retrieve some candidates, right? And currently it's had like these two stages: first retrieve some candidates, and then do some re-ranking, right, to get the final prediction. But now, as you pointed out, right, so, like most of the methods, they do this two steps somehow independently, right? So, but you can like use the one step to improve the other. It will be really interesting.
Yeah, but there are some challenges. I am trying to tackle them. But hope we can get good results in the large scale knowledge graphs. It's quite challenging compared to the Wikipedia FB 15K. The data set is quite small, and I think negative sampling really matters in large scale knowledge graphs.
Yeah, I think actually one follow-up question actually to all the three teams, even based on your point, is that have you guys ever like probably run the winner model on the regular OGB WikiKG data set, which is like definitely like smaller than this WikiKG 90 million, but it's still like a decently large knowledge graph that, I mean, it's still like much larger than the freebase. So than the freebase 15K. So I guess that's another pretty good test bed that you guys probably can try it out.
Okay, thank you.
Yeah, sounds good.
Try it later.
Yeah, we definitely intend also to explore other data sets with our model.
Okay, yeah, sounds good. So I guess one final question to all three of you is that, have you guys ever thinking about like use of graph neural networks in the link prediction task? Like, because like everyone is clearly like the winner solution, even the top 10 solutions, most of them are based on like knowledge graph embeddings, right? Where we don't have any message passing modules component in it. So I was just wondering about your thoughts on, is there any chance that we can use a graph neural network to do the same task with a similar performance?
I think that, yeah, this is a very good question. From my point of view, I think that this is something that in general the research community should look a lot into. Of course, there are, from a point of view, two problems in here. First of all, of course, doing message passing on graphs of this kind of scale is very, very computationally expensive. So there are a lot of limitations and scalability issues that arise when trying to pass from knowledge graph embedding models to models we use GNN encoders, for instance. And then the second point is understanding whether this is worth or not, because I mean, there was a paper that came out, I think, a few months ago from Michigan State, if I remember correctly, which was investigating indeed whether for this kind of tasks, GNN models can actually give improvements compared to standard knowledge graph embedding models, and the results seem quite uncertain in the sense that it's not clearly evident, at least on some of the data set, that one can get improvements using GNNs. So I think that there are a lot of questions still open in this direction, and I think that it's a very promising research direction.
Thank you so much. Yeah, I guess due to the time limit, we probably have to move on to the end this session. I want to thank you again and congratulations again to all the 3 winners. And yeah, let's give it up to them again. And now,
thank you very much.
Thank you
very much.
We hand it over back to Wei Hua for the next session.
Okay, great. Thank you, Hongyu. Can everyone see the screen?
Yes.
Okay, cool. So let's move on to the final graph levels track, which is called PCQ, which uses this PCQM 4 million version 2 dataset. And it is a dataset of molecular graphs, and the task is to predict the important quantum chemistry property called homolumo gap of a given molecule. And this can be cast as a graph level regression problem. To give you a bit of a background in chemistry, this homolumo gap that we're interested in predicting is computed using 2-stage expensive quantum calculation. First, we're given this 2D molecular graph, and we use hours of quantum calculations to optimize this 3D geometry to obtain the 3D molecular graph at the equilibrium state. Then, given this equilibrium state, we calculate this homolumo gap of this optimized 3D molecular graphs. And as we can see, this entire calculation is extremely expensive, and it takes the hours of computation per molecule. And our goal is to use machine learning to accelerate this quantum calculation. So we want to use machine learning surrogate model to make prediction of this homolumo gap given 2D molecular graph in much less than a second. And our dataset is created based on the amazing PubChem QC project, which has spent a significant amount of compute to calculate the quantum chemistry property of around the 4 million molecules. And these molecules are provided as the SMILE strings, as you can see on the left corner. And from these SMILE strings, we can construct the 2D molecular graphs, and this can be fed as an input to a graph machine learning model. In terms of the task details, we split the entire dataset based on molecule ID in the PubChem database, with a split ratio of 90, 2, and 8 for training, validation, test, respectively. And we provide the 3D molecular graphs on the training molecules on this 90% of this training molecule, so that these 3D structures may be utilized at the training stage. And at the test time, we do not provide this 3D molecular graphs, so that the test inference needs to be performed based on the original 2D molecular graphs. And for the evaluation metric, we use the standard mean absolute error, MAE. And for the inference, we limit the inference budget per molecule to be 0.1 second, which is 4 orders of magnitude faster than the original expensive quantum calculation. And this data set is really challenging. And first of all, it's obviously this is a massive data set with nearly 4 million molecular graphs. And to learn effective regressor over such a large number of graphs, we need to build and train very expensive GNNs to really learn from this abundant data set. And the second, our task does not provide the 3D molecular graphs at the validation test time, which means that the target property needs to be predicted based solely on the 2D molecular graphs. And this is very different from conventional QM9 dataset, which provides the 3D molecular graphs. And this basically means that our task is more realistic and meaningful because we do not assume this 3D molecular graphs to be provided at the inference stage, and obtaining 3D graphs is expensive in its own sake. Now we are excited to announce the winners of the graph level track. The first place winner is We Love Graphs team from Graph Core, achieving 0.0719 MAE score. We then have the tied second place winners. One is the BizNet team from Microsoft, and another is a NVIDIA PCQM V2 team, both achieving the 0.0723 MAE score. Congratulations to all the winners. Now let's move on to the winners' presentations. We'll have 3 winners presenting their solutions, followed by Q&A session. So first, let's welcome Dominic Masters from We Love Graphs team.
Good evening, good morning. Thank you all for coming. And I hope our team name represents the sentiment of not just us, but all the people here. I hope we're all very enthusiastic about graphs. Right. Can you see that?
Yes.
Brilliant. Okay, so I'm here to present our GPS plus model. This is a collaboration between GraphCore, Valence, and Mila, and I really just want to say thanks to all the people that worked on this. It's been a lot of hard work gone into this, but it's also been a lot of fun. So again, thanks to the organisers for setting up the competition. I hope people don't mind if I omit the obligatory data set slide and move straight into our model overview. So here I'm want to really talk about what's different between our model compared to some of the more the other methods in the literature. As the most significant difference is that we build a hybrid MPNN and transformer model, which really builds on the GPS framework that's been presented by some of our collaborators earlier in the conference. So the main contributions of this work is we build a kind of very significant MPNN component to our model to emphasize the local inductive biases available in the data set. We include 2 forms of global communication, both an attention module and a global feature in our MPNN. We incorporate the 3D features from the training set. We improve the default PCQM V2 feature set. And we also generate a very large ensemble to maximize our final prediction accuracy. All in all, our final model has 44 million parameters, and this achieves a single model valid MAE of 0.0778, which is very competitive with the other models in the literature. And our test challenge MAE is 0.0719, and this is over a very large ensemble of 112 models. And the other significant thing is that we use IPUs for all our training and inference. So before I get into models, I'd like to explain a little bit about the IPU and how it helped us in this task. So IPUs, how do they differ from kind of more conventional GPU hardware? The most significant difference is how the compute and memory is distributed across the chip. For GPUs, most of the memory is on off-chip DRAM, whereas with IPUs, we co-locate our compute and memory modules and distribute these all across the chip. The result of this is that it really maximizes memory bandwidth. So we achieve up to 65 terabytes of memory bandwidth accessing that memory, but also it allows us to very flexibly utilize the 350 teraflops of float 16 compute that we have. Now, there are a lot of subtleties in how that affects different models, but for GNNs, this has 2 major effects. One, that it really accelerates the sparse communication ops like gather and scatter that are very, very prominent in GNNs. But also we get very good utilization of matmals across a very wide range of sizes. Even matmals with smaller hidden sizes or smaller batch sizes, we can still get very good utilization, which really helps with some of the more complex GNN models. Now, what this means is that our final model takes just 3 minutes per epoch to train on 16 IPUs, which is comparable to about 4 A100s. And actually, for a lot of our development models, they were up to 20 times faster than that. So this really sped up our development and the speed at which we could experiment with new models and our pace of research. So moving on to the model. This is our GPS++ model. So how this works is we just kind of start with our molecular description. We're going to build a range of input features from that, both 3D and other. We're going to encode these into global, edge, node, and attention bias features. Then we're going to pass these through our GPS module. Now notice that we have both message passing neural network and an attention module in there that are run in parallel. We do 16 steps of this, and then we kind of then goes into our loss. Now I think there's lots of complexity, lots of things that we've built on to get to the stage that we did. And I think one of the big questions that naturally comes out of this is which are the most important and how much do they affect our final results. So throughout this presentation, we're going to start with what is a very basic model and build up with the different features to finally get to our final GPS++ model, hopefully understanding a little bit more about how the different features impact our final results. So to start, we're going to start with what is a very simple model where we're going to have very simple input features, and our kind of compute component, our main component, is just going to be a simple GCN applied 16 times. Now this achieves a very reasonable valid ME of 0.0943, but of course is going to get nowhere near the top places in the leaderboard. So to start off, I'm going to start with one of the areas that we really focused on, put a lot of work into, about how we can improve that GCN with a more with a kind of more powerful MPNN. So here, to start off, this is a representation of what the GCN looks like in terms of the compute. Importantly, I've highlighted the gather and scatter operations. These are often quite expensive on GPUs, but are really cheap for us to do on IPUs. And this gives us, the 0.0943 accuracy we highlighted before. The first thing we do is a fairly standard improvement is to add edge features. We found this really gave a very big improvement. One of the things that we've done differently to other people is that we actually use a smaller latent size for our edges than we do for our nodes. Our nodes are a latent size of 256, but our edges are of 128. We actually found this gave us a better result, but also really helps with the efficiency of the model. Secondly, we added more connectivity between the node and our edge path in our model. In particular, adding information going between not just from our senders to our receivers in our edges, but also the other way around, which meant that our message could essentially be built based on more information from both our senders and our receivers. This gave us, again, quite a considerable improvement in our results on our MAE, getting us down to about 0.088. And then we also added quite a small global latent, so only 64 latent. We only have one of these per graph. And then we're going to concatenate these to our node and edge messages that we're passing through our model. And I think we were really surprised about how much improvement this gave us for quite a simple improvement. And then finally, our two-layer MLPs we're using everywhere. We started using ReLUs, and we also found that using a GELU improved that performance. The next improvement we did was adding attention. So we did this, we added this in parallel using the framework described in the original GPS paper. This gives actually a comparably small improvement compared to adding to our MPNN improvements. We next added the bias that was used in the graph former paper. So this is the shortest pass distance that biases the attention to nodes that are closer in the graph. Again, actually, surprisingly, this didn't improve things as much as we expected. And then finally, for the attention model, we added an MLP after it, which again improved things. But actually, one of the most interesting things here is we found that the attention really didn't help us as much as we expected. Now, in a competition environment, of course, this is something that we want to have every benefit we can. And we do expect that this could be improved in other ways. But we're a little bit surprised about the size of the improvement here. So another area that is quite common in a lot of the GNN and molecular research is to add structural input features. So this are things like these eigenvectors of the graph Laplacian or random walk probabilities. So what's the probability of taking a k-step walk and landing on your own node? These are generally quite cheap to do in the compute stages and gives a reasonable improvement to our MAE. Again, another area in the input feature space that's really improved things, maybe to a surprising extent, was adding more chemical input features. So you can see the table here with the PCQ data set. We have this set of features described on the left-hand side of the table. And I guess our initial intuition was, well, the more we add, the better it's going to get. And we really tried this. We tried adding lots of things, adding everything we could think of. And what we really found is actually just led to significant overfitting. And in the end, it resulted in quite a lot of hyperparameter sweeping to get to this result and a fairly careful choice of input features. But doing that did really give quite a significant improvement in our MAE. So going from 0.084 down to 0.082. But I think the thing that I would say, a kind of word of caution, is that actually, removing features was as important as adding features, we found, to getting that result. And then what we also did is we added a noisy node denoising regularization that was used in one of the last year's submissions, which we again found gave us a small improvement. So the next stage to improving our model was how we incorporated the 3D features. Actually, interestingly, I think this method is one that's common to all three of the top three submissions in this year's task, based on the paper, the Transformer M paper that came out about a month, but I think it's about a month before the final submission. So there's obviously lots of work from all the teams to incorporate that. But it really was trying to get over the challenge of how to get the benefit of the training of the 3D conformers in training without requiring them in validation and test. So the method that they describe is to group, to kind of define different groups of input features. So we have some that are, this 2D attention bias is one that we do have available the whole time. And whereas 3D features we'd only have in training and not in validation. So what we're going to do is we're going to define this group one is just the features that we have available in test time. Group two is just the 3D features, and group three is all the available features in those training steps. And then we're going to sample those. Actually, that should be 0.2, 0.6, and then 0.2 for the final for group three. And then we're going to sample those with that probability for each sample. And then in test time, we're always going to use this group one, which is the features available at test time. Now, the next question is what 3D features are we going to use? So what we do is we take the 3D conformer, and of course, one of the most important things about the features we generate is that they're translationally equivariant. So the most obvious way to compute those is to use distances. So initially we calculate the distance matrix, so the distances between all the node pairs. And next we put that through a Gaussian kernel function. Essentially, this just projects our scalar property into a vector space. Then we create three different types of 3D features. One is for any of those pairs that represents an edge. This defines the bond length. So we use this as an edge feature. This has a small benefit, but not enough to show up on this table on the graph. The next one is that we actually take the sum across one of these axes of these features. and this defines a node feature. And finally, we use the distance matrix as another bias to our attention. And again, the thing that's when we went into this method and started using this method, we really expected the distance matrix bias to be the most important part of this. But actually, we found that the 3D, the sum across of the distances that we use as a node feature had a more significant impact on our final MAE. Now, the final set of improvements we did is one is to increase the training time. So all of these ablations have been done with 200 epochs, increasing that to 450 epochs gives a small improvement. It's a lot more expensive, so you might not want to do that in a normal situation, but for a competition environment, we're going to take any benefit we can. And then also we're going to do as much ensembling as we can. So in our case, there was our ensembling strategy had 3 different elements. One is we're going to train on all the available data, so training and validation. And actually the masking approach that we showed in the previous slide really enabled us to use that validation data as part of our training set. And we think that was really important in getting our best result. Next, we used 7 different kind of high parameter variations. They weren't super different, but fairly small variations to our high parameters. And then finally, we calculated, of these, we calculated a total of 112 independent models and ensembled those. So it was a really large ensemble that we did. And of course, this was really massively helped by IPUs and the fact that training each of these models for 450 epochs took less than a day on a server of 16 IPUs. And then even more, that the inference for each of those models across the full test set only takes about 18 seconds on a single IPU. So this meant that we could complete all of our ensembles well within the 4-hour inference budget. So to summarize what we found in the conclusions, I think that one of the most significant things we found is that the MPNN module had a really significant impact on the result. And I think this was a little bit in contrast to a lot of the recent research in molecular modeling that have used a lot of transformers. And we kind of expected the transform element to be the most significant part, but we really found that the MPNN was the most significant part of our model, and we could get pretty close to our final single model performance without using any transformer elements at all. Next, we found that optimizing input features was really beneficial. It took a lot of high parameter sweeping, and we had to be quite careful about overfitting. But in the end, in terms of the actual model speed, it was very cheap way to improve our performance. The 3D features, again, added a really significant benefit to our final MAE. But then I think the most significant part of this was using a very large, diverse ensemble. That really led to a very large improvement in our final MAE. And then just to kind of end the conclusions, we really felt that the IPUs allowed us to train what is actually a very complex architecture extremely quickly. And it wasn't really just about being able to do lots of ensembles or things like that, but it's really drastically improved the pace of our research, enabling us to do lots of high parameter sweeping, test lots of model variants, and this is really one of the main reasons why we think we were so successful. If anyone is interested in using our model and testing our IPUs, we're now making them available for free, or at least for a kind of limited period of time. So just follow these links. You can try some notebooks which show both training and inference of our GPS++ model. So yeah, we're really interested for more people to try things and for more people to do research on IPUs. That's everything. Thanks for listening. And I'll just leave you with an image. This image is actually a representation of the compute graph of our GPS++ model as generated by our popular compiler. So that's kind of describes the model that we've run.
Thank you, Dominic, for the wonderful presentation. A lot of insights and evaluation studies, and they're super helpful. Thank you so much. Next, let's move on to the presentation by BizNet. It will be presented by Tom. Tom 1, are you here? I think I saw him. Okay. Maybe we can first go to the NVIDIA team, and then I'll come back to see if Tom is here. So let's move on to the presentation by NVIDIA PCQM version 2 team, and it will be presented by Jean-France Puget. So Jean, please.
Hello. Okay. Let me share. You see the slide?
Yes.
Okay. So we are a not so large team. I'm Jean-François Puget from France. The reason we entered the competition, first we entered a bit late, too late. So if there is a new one, we'll enter earlier. Because colleagues Sajad and Alexandre were working on a NVIDIA implementation for GraphFormer, which was one of the best model published in the middle of the competition. So they had this implementation, and they started exploring variants. They asked us to join, so I'm leading a small team of Kaggle grandmasters. So we create models, and we started creating new models with the hope that ensembling diverse models would help. Then Transformer M was published, as the other teams we noticed, and good news, it's an evolution of GraphFormer, so it was rather easy to add the 3D part and explore variants. So our solution, our solution is an ensemble of very diverse models. So you have Transformer M variants. I will explain which variants. And at training time, the input molecule graphs computed from RDKit, from the smiles, and also the 3D data. Then we have a direct GNN implementation using PyTorch geometric on the molecular graph. We also have another transformer that works on a different graph where basically the chemical bonds and the rings are also nodes. And this may surprise people here. We also added some image regression models. So we generate 2D images using RDKit and just run a computer vision model to predict the gap. And it's interesting that just using images, we can get to a validation of 0.1 or something like that. So it's not competitive with Transformer M, but it's good enough to add in the ensemble. And then for ensembling, we took a linear model with a loss that is close to MAE, so a Huber loss, to make the predictions. Early in the competition, we noticed that there was a distribution shift. It was discussed a bit in one Git issue, but we found it significant. Basically, in trend data, you only have molecules up to 20 atoms. And this histogram is log scale. So the bulk of molecules are here. So they are well represented in train, but there is still a medium tail, I would say, of larger molecules that only appear in valid or test sets. And we did test, we submitted in the test challenge a simple, the PyTorch geometric model trained just on the original train or on all data to see the effect of training on the larger molecules. And it was significant. It was a 10% improvement in MAE. So we decided to resample. So take the union of train and valid and use k-fold cross-validation. And we created folds to have a size similar to that of the test sets, which means 24 folds. Ideally, we would train each model 24 times, but for sake of time, and we saw that scores were data is large enough that we don't need to do all folds, basically. So we trained on 4 folds. So for each model, we train 4 times on 4 different folds. And we use the validation predictions of these 4 models as input to train the Huber regressor. So that's called stacking in let's say in Kaggle folklore, and it's a way to ensemble that is a bit more powerful than just taking the average. Basically, you get a weighted average, but the weights are computed by machine learning, not by hand. I will show the weights we get at the end. Transformer M, as I said, we already had implementation of graph-former variants, and we just extended those variants to the 3D part of Transformer M. So first variant is to vary the number of layers, so 12 or 18. The second one is to vary the distribution of training steps with 2D only, with 3D only, or joint training. So these are really common variants. Stochastic depths, so where you skip at random. It's like a dropout, but at the layer level. This is also a common technique. Another one that we did that is more specific to this problem is we computed 2 sets of descriptors for molecules based on published papers. We have I put the reference in the report. Should have put it here. And then we added these 2 as additional targets. With an additional loss. So this drives a model a bit sideways compared to the other, and it adds diversity. Then using the denoising auxiliary target or not that was used in Transformer M. Train on all data versus training on folds. So we did train few models on all data. I did not put the training details because we mostly just followed Transformer M, which was the same as GraphFormer as far as I know. And on the right, you see the validation for our folds. So best ones are around 7.4. So this line is Transformer M, well, our code for Transformer M. And you see variants. Some variants are a bit better, some are really similar, some are a bit worse, but they had diversity. So we did not ensemble as many models as previous team. I believe that's one, or if not the only reason our score is a bit worse. Then we have other models, so I will describe this molecular transformer. It's a bit worse, but this one is not trained using 3D. And then we try different computer vision EfficientNet B3 was better, but when we assembled, it did not help as much as ResNet, so we dropped it. Molecular transformer, the idea is quite simple, and it's a bit similar to some published models. The idea is to represent the structure of the graph by explicit nodes. So create, as usual, a global node for the molecule, a node per atom, so far so good, a node per chemical bond, and a node per cycle. So number of cycles can be exponential in the size of the molecule. So RDKit has something called SSR, a smallest subset of rings or something like that. So we use that. So it's a sample of the cycles that covers as many atoms as possible. And then edges on that graph are just natural edges. So for instance, for a chemical bond, you would have an edge between the node for the bond and each of the two atoms. And you also have an edge between the two atoms directly. And for rings, you basically have an edge from the ring node to each of the atoms. I tried having an edge between bonds that appear in a ring and the ring, but it did not help. And that's about it. Then we just apply a transformer on that, and we mask attention by the edges as described. So nothing fancy. The embeddings, we just take the embeddings proposed in the data set. If we had a bit more time, we would have looked, because some features, I'm thinking about chirality. This seemed to be a bit problematic, so maybe we should have dropped it. Anyway, so we use just the provided dataset features plus the atom degree for nodes. For bonds, same, we use the 3 features provided by the dataset, and for rings, we just use an embedding of the size of the number of atoms. And then it's a vanilla transformer with one modification. We repeat the feed-forward network after each attention. So instead of having one attention layer, one feed-forward, we have one attention, 2 feed-forward layers, and we repeat 12 times. And the output is computed from the global node last layer output. And surprisingly, so there is no shortest path bias. There is no edge bias. And this simple transformer scores better on the original valid data set than Graphformer. So that was a bit surprising to us. Yes, something I did not, you can see that these numbers on previous one, 7, so 0.074 are significantly better than, say, previous team reporting 0.077. It's because these are our folds. If we look at the original validation data set, so train on the original train and compute ME on the valid, we get 0.077, which so it's a bit higher using, and this is because of the distribution shift. Remember, the training data has no large molecules. Image, so that's the actual code of the model. I'm not kidding you. There is a package for computer vision for PyTorch models that is called PyTorch models or team on Git, and it's the most popular PyTorch image repo. So you have a number of models. You just need to give the model name, and that's about it. And then a regression head, and that's it. So these are standard computer vision techniques. You train, for instance, by doing data augmentation. So in for when you have 3D molecules, data augmentation, a natural one is to add noise. So that's the denoising auxiliary task. For images, you can just flip images left, right, top, bottom. You can also scale them a bit and or rotate them. Training is slower, however, especially if you enlarge the images. But models are smaller in number of weights. Our models are, so with 12 layers, there are 43, 44 million weights. So same as any other transformer.
Jim, you need to
Yes.
wrap up. You're running out of time.
That's my last slide. So you see on the right the weights. So transformer M average is an average of all these models. You see that the weights of the image and the PyTorch geometric is small, but I believe thanks to them we tied second. Without we would be third. And that's it.
Cool. Thank you so much for the great presentation. It's very interesting that you tried so many models from different application domain, like not only graph neural network, but also like convolution and
yeah.
Very interesting. Okay, I saw Tom is coming back. So Tom, please take it away.
Okay. So I will share my screen.
Tom, can you hear me? I think you're freezed. Can everyone hear me?
Yeah, I can hear you fine.
Oh, you can hear me. So Tom is freezing, right?
Yeah, he's frozen for me too.
Yeah, we lost him.
Okay, we lost him. Interesting. Looks like his internet connection is not so good. But maybe instead of waiting for him, because we're also running out of time, let's keep his presentation toward in the end, and let's move on to the Q&A session first. How about that?
Okay, sorry.
Oh,
I'm
you're coming back. Okay,
I'm coming back because the network is not very good. Sorry for that.
No problem. Then you don't need to share your video. Just share your screen.
Okay.
Okay.
So now can you see my screen?
Yes.
Okay, cool. Good evening and good morning, everyone. This is Tong Wang from Microsoft Research AI for Science. On behalf of our VisNet team, I will present our solution for OGB-LSC graph level track challenge. For the graph level track, the task is to predict an important quantum chemical property, the Huma-Luma gap, given a molecule. The Huma-Luma gap is calculated based on the optimized structure of the molecule. And the difference between the training and the inference processes is that the optimized 3D structures are available in the training set, where there are only 1D smells or 2D topology provided for the validation and the test sets. For this task, we defined two. The first one is how to efficiently model molecular representation. And the second one is how to bridge the gap between the 2D topologies and the 3D optimized structures. So our solution is an ensemble based on the equivariant model WISNet to tackle the two challenges. On the one hand, we adopted our recently designed equivariant graph neural network WISNet to efficiently and elaborately model the geometric information from molecular representation. On the other hand, we trained two kinds of our models, Transformer M WISNet and pre-trained 3D WISNet to bridge the gap between the 2D topologies and the optimized 3D structures. So next, I will make detailed illustrations from these two sides. In our recently designed WISNet, we propose a novel effective directional information calculation paradigm, the runtime geometric calculation, to introduce the angle and the dihedral information in the vector-based equivariant graph neural networks. As shown in this slide, for each node in the graph neural network, we first define the direction unit, Vi, which is the sum of all directional information of the first order of neighborhoods of node I. Thus, the direction unit can act as a vectorized representation of node I. Then we deduce the angles with the vertex of node I from the inner product of the direction unit Vi. These equations show the inner product of the direction unit Vi represents the sum of all cosine values of all angles between the node I and all its first order neighborhoods. Thus, we can get the angular information from molecular graph with only linear complexity. Next, we can also deduce the calculation of dihedrals based on the direction unit. Dihedral is derived from the inner product of the projections of the direction unit Vi and Vj. As shown in the figure, first, we calculate the direction unit Vi and Vj for node I and node j respectively. Then we calculate the rejections of two direction units on the vector Uij. The inner product of two rejections represents the sum of all cosine values of all dihedrals with the rotation axis Eig. Since we calculate the geometric information from the directional unit, which only sums the vectors from the target node to its neighborhoods, only once the computational complexity remains On rather than n cubic or n biquadratic. So after efficiently encode and calculate the key geometric information, we then propose a novel vector scalar interaction message passing to fully utilize the information for molecular modeling. Our vector scalar interaction message passing consists of two parts. So the first part is the scalar to vector process as shown in the figure and the equations. We use both the scalar message and the vector message to update vector representation, the direction unit Vi. Then is the vector to scalar process. By the runtime geometry calculation module, we calculate the inner product of the direction unit of each node, and all angle information is updated to the scalar representations of the intersection node Hi. Meanwhile, the inner product between the two nodes, node I and node j, are also calculated, and thus all dihedral angles is updated to the scalar representation of the intersection edge Fij. So taken together, the equivariant WISNet can efficiently and elaborately model the geometric information for molecular representation, which addressed the first challenge. And for the second challenge, based on WISNet, we designed two kinds of models, Transformer M WISNet, a hybrid 2D and 3D molecular structure training based on the Transformer M. And the pre-trained 3D WISNet, it is a pre-trained WISNet by distilling the geometric information from the optimized structures. For the Transformer M WISNet, we take both the molecular topology and optimized structures for model training. Since for all angles calculated in VisNet, the intersection is a central node. So in the input layer, we incorporated the RGC angle module in VisNet as the additional node features. Also, like the RGC angle, the tangles is calculated in VisNet share the same rotation axes between node I and node J. Thus, in each transformer block, we incorporated the RGC tangential module as a bias item to calculate the attention score between node I and node J. In our computation, another idea to bridge the gap between the 2D topology and the 3D optimized structure is to generate a 3D structure by RDKit and then distill the knowledge from the optimized structure to the generated structures during model training. Thus, in pre-trained 3D VisNet, we first trained a VisNet taking the optimized structures as the input. This model can achieve very small mean absolute error. Then we use the model to distill knowledge to another VisNet that takes the generated structures by RDKit as the inputs. And for the student model, we also adopted the physical chemical properties of the molecules as the input. Furthermore, the teacher VisNet guided the student VisNet by the contrastive loss function calculated on the graph representations of the representative last layers. Taken all together, we made an ensemble with 20 transformer M VisNet and 2 pre-trained 3D VisNet. For each kind of models, variance was trained with different hyperparameters as shown in these tables. The ensemble achieved an MAE of 0.0723 on the test challenge set. Finally, I sincerely appreciate our all team members, Yusong Wang, Shaoning Li, Dr. Zun Wang, and Xinheng He for their great works during the competition. Furthermore, Dr. Bin Shao and Dr. Tian Liu for the great guidance and support. In addition, we are also hiring full-time researchers and full-time software engineers and research interns on graph neural network, molecular dynamic simulation, and quantum chemistry. So this is all the presentation of VisNet team. Thank you.
Thank you so much, Tom, for the great presentation. Now I think we're running out of time, but let's move on to the 10 minutes Q&A session among all the winners. So if you can open the video, that'll be great. I think the question that I have for all the winners is that what is the biggest challenge when you tackle this data set, and what is the biggest surprise or learning that you have through this competition to all the winners?
I'm happy to go first. I think challenges. I think one of the challenges we had was, because we were building this hybrid model that was a little bit different to what else was in the research. We kind of had all the standard research problems of having to do a lot of testing, a lot of high parameter sweeping, a lot of, and it was, there's a lot of challenges in trying to get to the result that we got to. It was really a lot of work from our team. And the second, kind of challenge as part of that was really the 3D data was quite hard to incorporate. We tried a number of methods, and I think a lot of, as with other people, the Transform M paper was extremely useful in helping there, but it was also quite new. I expect to see other ways of incorporating that data in the next over the next year. So I'm really interested to see that. And in terms of the surprises, I think the biggest surprise to me was how difficult it was to improve the result by just increasing model size. In so many other areas, you increase model size and you just get a benefit. And we tried, and I'm pretty sure, and would imagine that the other teams tried as well. And it wasn't simple, and it's not easy. And maybe I think that might mean that the data set size, we really need even larger data sets than we've got. I think one of the difficulties with molecular data is the kind of classic augmentation methods are much harder. You know, with images, we know we can just augment it and increase our data set size that way, and it's much more difficult molecules. Yeah, it feels like we need even bigger data sets, which is I know challenging for many reasons.
That's a great point. I agree. Like a transformer M is an excellent idea, but it's also quite simple. Like you add several terms and you have different terms at different groups. So I agree. Like it's surprising that that's such a simple idea works well, and it's really common across all the team. I assumed maybe you have tried other ideas before this paper comes out, but looks like this is the way to go, at least for now. That's pretty interesting. And data augmentation, it looks like in your experiments, the noisy nodes, is that in your presentation? That works, but beyond that, like no data augmentation works.
Yeah, it was helpful. That was helpful, but yeah, it was only a small benefit.
Okay, sounds good. Thank you so much. Jin, do you want to share?
Yeah, challenge. So I mentioned the distribution shift. Another challenge is that the same smile could occur more than once with different target values. So you have different conformers of the molecule, probably.
Right.
Which means we had to match the 3D, to align the 3D to the right conformer. So it was, I think this part of the data set is a bit,
right.
I believe actually that the 3D representations, so when a smile occurs several times, you did not report the 3D data in the same order as
right.
The chirality and blah blah. So the 2D and 3D representations are not aligned when there are more than one conformer, I believe.
That's a great point. And I think we've improved that from the version 1 of the PCQM, where we actually derive from the 2D molecular representation from the optimized 3D structure. But yeah, that's which actually improved the model performance by a large margin from the version 1. But I agree.
But still, if you run it again, it should be made clear when there are several conformers. So when the same smile occurred several times with different targets, may be real sure. So maybe 20 days that the 3D data really maps to the right target.
Right.
So that was a small challenge. And actually, I must say, we tried. It happens that the same smile occurs in test and in train. So we have the target value for these. So we did estimate, was it a good idea it's not cheating because it's using data.
Yeah.
But when a smile occurs in train, to use a train value. But the variation of target for same smile was large enough we didn't use it. We didn't. But this is a leak. We call it a leak in Kaggle, for instance. And if we really squeeze, maybe given how close the top 3 teams are, exploiting this leak could have moved us ahead, for instance. And it's not something you want, right? This is not advanced science. So if you run it again, be careful about this leak. So same smile in test and train.
Okay. And the same smile, but different values.
That's why we didn't use it, because we noticed that when same smile occurs in test, it has values that are far apart enough not be useful. But still, maybe if we had spent more time on this, it can give an advantage, which is not useful in practice.
We can take it in our part on our side. Thank you. Great. And Tom, do you want to share some?
Yes. From my point of view, I think the biggest challenge is how to bridge the gap between the 2D topology and the homologue gap derived from the optimized 3D structures. So you know the training set has optimized 3D structure, so the prediction is very easy. So, but during in the validation and the inference, during the inference on the test set, we only have the 1D smells. It is easy to get the 2D topology from the 1D smells, but it's very hard to get the optimized structure from only 1D smells. So I think it is a basic change. From our evaluations, we found if we have the optimized structure in the training set, we can make a very accurate predictions for these molecules. For example, in our model of the VisNet, we can achieve about 0.02 0.025 or 0.027 performance on the training set. But if we do not have the optimized structures, the test set is very challenging. So this is a basic challenge. So during the whole process of our participation, our main attention is focused on how to bridge the gap between two of them. So we tried many approaches. For example, the pre-trained strategy. We pre-train a model to distill the knowledge from the optimized structures to the generalized structure by RDKit. This is an alternative choice. And another alternative choice, is transformer M that bring a very reasonable way to train the 2D and 3D information in a same deep neural network. And we also tried some other strategies, for example, the diffusion models to generate the optimized structures from the 1D smells or from a initial structure generated by RDKit. But since the training process is very complex, during the competition for our submission, we didn't submit the model of the diffusion trained by diffusion strategy, but we think the diffusion model or other generative model strategies is also some alternative ways to bridge the gap in the future.
Yeah, that's a great point. I mean, it's the most natural idea would be from 2D graph to generate 3D graph and then use that as input. And that was kind of the most natural idea, and I hope that direction can be pursued further into the future.
Yes, exactly.
Thank you so much. Thank you so much. And I think we are running out of time, so I want to ask if audience have any questions, or among the winners, do you have any questions to each other? If not, I think we can conclude the session.
I just want to congratulate the two other teams. They gave us hard time.
Thank you very much. Appreciate it. It was very close very close in the end. So yeah, it was really good. And thanks to the organizers as well for setting it up.
Yeah,
so much
quality data.
Thank you very much. Thank you very much for the organization, and thank you for all winners to make a very good presentation.
Yeah. Congratulations to all the winners, and thank you for the great presentation. And if there's no more question, I'm going to conclude the session. Thank you everyone for attending. Thank you so much. Have a nice day. Bye.
Bye.
Okay, bye.